In some diamondiferous terrains, stones that look like dark rubble, nondescript greasy surfaced, sometimes pitted, can signal pipes worth millions. But the surface gives little away. That's why the majority of near-surface indicator clusters remain untested, even in places with known diamond potential. These stones don't flash like gems or shimmer like gold. They sit inert in dry creeks, behind road cuts, or embedded in gravel bars, often just steps away from paved roads. What sets them apart is microscopic rather than aesthetic. Most commonly, the key signal is their mineral company. Not diamonds themselves, but fragments of rock that diamonds form within. These include weathered kimberlite or lamproite nodules, rock types that, over time, break down to look like common claystone, serpentinite, or friable basalt. To the untrained eye, there's nothing glittering here. But dig into a pocket of material just beneath the oxidized surface, and suddenly, a few things shift. The texture becomes crumbly and ultramafic, the smell earthy metallic. There may be soft blue-tinted material known as blue ground, or hints of crater-fill breccia. These deposits often lie at the margins of ancient cratons, geological shields stable for over 2.5 billion years. They tend to erode slowly, meaning any surface hint could trace back to a vertical pipe hundreds of meters deep. The diamond-bearing zones themselves are rarely exposed. Erosion only reveals traces. The true value comes from connecting these surface crumbs to deeper hosts. And that means starting with the kinds of rocks most collectors ignore. One particular misjudgment happens in glacial or alluvial terrains where transported rock fragments can carry indicator signatures far from source. Here, what looks like drift rubble may in fact be a kimberlitic fragment, a chemically altered, manganese-rich pebble with embedded garnets or ilmenite grains. Even a tiny 3-centimeter sample, if analyzed, can confirm a diamond-bearing parent pipe upstream. But without that trained suspicion, the find is discarded as uninteresting slag. In multiple documented recoveries, diamonds were first found not by glamour seekers, but by industrial surveyors cataloging unwanted overburden. The average finder skipped right past what mattered most. Which begs the real question: what should we actually be looking for, visually, before any tools come out of the pack? The critical distinction between ordinary rubble and a potential diamond host often comes down to how the stone handles light and how it breaks. Most field searchers rely on color or sparkle, both of which are misleading in diamondiferous contexts. Instead, seasoned prospectors read the surface texture and break pattern. Dull can be good, greasy is better, and certain fracture habits scream look again. Start with luster. While diamonds themselves are famously adamantine, the rocks they form in, especially kimberlite and lamproite, tend to exhibit a muted, greasy, or earthy luster when weathered. These stones rarely shine outright. Instead, they reflect light inconsistently, often with a slick or wet appearance that doesn't match their dry environment. This can appear in both cobble-sized nodules and fine gravels, particularly after rainfall. In sunlight, they may look like moist clay that doesn't dry, an optical cue often mistaken for low-grade serpentinite. Then there's fracture habit. A promising sign is when a stone breaks unevenly, in a way that doesn't align with typical sedimentary or igneous patterns. Kimberlite, for instance, tends to crumble or splinter with a friable, gritty break, often revealing embedded crystals of olivine or garnet. These inclusions may be dark red, black, or olive green, tiny but diagnostic. In contrast, lamproite often displays a more vesicular texture, sometimes confused with scoria, but with less uniform pore distribution and a slightly greasy matrix. The difference becomes clear under a hand lens. Vesicles in lamproite are less regular and more clay-filled, often tinted buff or ochre. Another visual signal lies in the presence of weathered spinel or ilmenite grains, small black, metallic dots that resist the surrounding stone's erosion. These can appear as peppery inclusions on broken surfaces, particularly in stream-rounded cobbles. Unlike ironstone, which may rust or develop a flaky surface, kimberlite-derived rocks retain a compact, dense look even when oxidized. But perhaps the most missed tell is translucency. Not in the stone as a whole, but in isolated mineral fragments. If you break a candidate rock and find translucent red or pink grains, test them. They may be pyrope garnets, a high-chrome variety closely associated with diamond pipes. These grains resist weathering and often remain trapped in creek beds or overbank deposits, glinting subtly when wet but vanishing in dry screens unless specifically sought. The ordinary eye dismisses these rocks as weathered junk. But the right kind of dullness, the odd oily glint, the peppering of tiny dense minerals, all add up to a short list worth testing. So before any lab gear or thermal probes, the trained eye starts here, with light, break, and habit. Yet even a promising surface can deceive. So how do we know when a stone's clues warrant the next step in the field? Even the most promising rock means little if it's found in the wrong geological setting. That's why the first serious filter isn't what you see in your hand, but where your feet are. Diamonds don't occur randomly. They're tied to ancient geological events and transported by specific rock-forming processes. Recognizing the right terrain is the difference between wasting days on river gravel and identifying a viable source pipe. The prime zones for diamondiferous material are called cratons, stable continental cores that have remained tectonically undisturbed for billions of years. Most of Earth's economic diamond deposits are found in or near these cratonic shields. Within them, volcanic events from deep mantle origins carried diamonds to the surface in fast-moving magmas, forming vertical pipes of kimberlite or lamproite. These pipes, once eroded, leave trace materials scattered across a wider zone, but only within certain hydrological and erosional patterns. Look first to paleochannels, ancient riverbeds no longer active. These often lie beneath current sediment layers or adjacent to escarpments and old terraces. If these channels intersect known cratonic zones, there's a good chance they trap diamond-bearing detritus during past erosional cycles. Over time, these deposits become buried under sand, gravel, or clay, and may only be exposed by modern cuts, roadwork, mining activity, or stream incision. Such exposures can yield placer-style diamond concentrations in secondary settings. In contrast, active creeks and rivers can still carry diamonds, but usually in low concentrations unless directly downstream from eroded pipes. These are rarely worth large-scale recovery unless historic grades are documented. Instead, look for spots where flow slows abruptly, behind bends, at confluences, or on the inside curve of meanders. Diamonds are dense, SG 3.52, but small, and they behave like fine gold or garnet in moving water, concentrating in micropockets and trap zones. Slopes matter too. On footslopes or eroding hillsides in known terrains, one might find boulder fields or colluvial scatter from disintegrated pipes. These deposits are subtle and tend to mix with other ultramafic rocks, making them hard to distinguish without testing. But when combined with mineral indicators, especially garnet or ilmenite, they provide a direct breadcrumb trail back to source. Surprisingly, some of the richest surface clues show up in areas people ignore: road gravel stockpiles, tailings from unrelated mining, or abandoned quarry floors. If these materials were sourced near cratonic zones or transported from suspected kimberlite regions, their byproducts might contain overlooked fragments. Several discoveries in Africa and Russia originated from such misclassified waste. Before any test kit or sampling gear is deployed, the smartest move is to check the terrain's age and structure. Is it Archean? Does it sit on or near a known shield like the Kopval, Slave, or Siberian? Has it been glaciated? And could that ice have transported fragments from source pipes? These are the macro questions that turn one rock into a field lead, or into a meaningless souvenir. Yet even in the right terrain, the stone must speak a specific language. Which brings us to the critical mineral trail. Tiny, heavy, often missed, but always pointing toward diamond potential. In diamond exploration, the stones themselves are rarely your first find. It's the minerals that ride shotgun with them. The subtle, dense fragments hidden in riverbeds, dry washes, and erosion fans that serve as the real clues. These are called indicator minerals, and their presence in sediment tells you that diamond-bearing rocks either weathered nearby or were transported into the drainage system. Yet to the untrained collector, they look like little more than black grit or garnet sand. The most important indicators are specific to kimberlite and lamproite pipes. Chief among them are pyrope garnet, especially G9 and G10 types, chromite, ilmenite, and magnesium-rich clinopyroxene. Pyropes are typically deep red to purplish and can show a faint translucency under good light. They're often rounded from transport, but retain a vitreous luster when wet. Ilmenite appears as metallic black grains, often with a slight blue or bronze tint, and is denser than most surrounding sediment. Chromite is similar in appearance, but tends to be duller and more granular. These minerals don't form together by accident. Their assemblage is a geochemical signature of a deep mantle source, where diamonds also originate. To find them, a collector needs to work small. Use a classifier or sieve set, preferably mesh sizes around number 20, 0.85 millimeters, and number 40, 0.425 millimeters, to concentrate sediments by size. Target drainages that flow across or away from suspected ultramafic terrain. Once isolated, heavy minerals will concentrate in the pan's bottom edge or along the back riffles of a sluice. In dry terrain, a simple battue or air sifting over a white tray helps separate the denser grains by visual contrast. A magnet is an underrated tool here. Ilmenite and magnetite are weakly magnetic, and a simple neodymium magnet passed under your pan or across a plastic plate can help tease out the dense black grains from quartz sand and mica flakes. Don't discard the non-magnetic residue too fast. Pyropes and chromite won't move, and they're just as vital. One mistake many make is to assume garnet equals diamond. But garnets are common across many rock types. The key is the sweet. If you find pyrope garnet with ilmenite and chromite, especially in a cratonic setting, you may be dealing with a dispersal train from a pipe. If only garnet is present, and it's almandine or grossular, typically brownish red or orange, it's more likely from metamorphic rocks, valuable in their own right, but not diamond-linked. Record keeping is critical at this stage. Every positive indicator sample should be GPS marked and compared with upstream sites. This lets you backtrack the dispersal gradient to its strongest point, potentially pointing you straight to the eroded surface trace of a hidden pipe. It's slow, meticulous work, but every major diamond discovery that didn't rely on aerial magnetics or drilling began with indicator sampling just like this. Still, indicators aren't enough. You need at least one more layer of confirmation before the diamond claim is more than a hopeful hunch. And that's where the first sampling pass comes in. A low-cost field method that tells you whether to dig deeper or move on. The first real test of a site's diamond potential isn't a lab assay. It's a deliberate, low-cost sweep using simple tools and trained observation. The goal isn't to find diamonds outright, but to determine whether the mineral indicators appear in meaningful concentrations and configurations. Done correctly, this pass can eliminate 90% of false leads in a single afternoon. Start with a transect approach. Define a 50 to 100 meter stretch along a creek, dry wash, slope, or road cut. Any location where water or gravity naturally concentrates material. Focus especially on inside bends, base of slope catchments, and low-energy zones where dense particles can settle. Collect small sediment samples, 1 to 2 liters, at regular intervals. Every 10 meters is standard, keeping depth and substrate consistent. Use a number 20 sieve, 0.85 millimeters aperture, to concentrate each sample. The objective is to isolate the heavy fraction, dense mineral grains that remain after light silicates, organic matter, and silt are removed. In water-rich zones, a simple gold pan or battue allows for effective winnowing. Work slowly. Once the top layer is rinsed off, examine what remains in the bottom groove. You're looking for chromite black grains, garnet red flashes, or tiny metallic flecks, especially those that don't float or flake. Once separated, dry the concentrate and use a neodymium magnet to pull off magnetic material. Ilmenite and magnetite will respond weakly but consistently. Observe the color and shape of what remains. Rounded red grains may be pyrope garnets. Angular opaque grains may be chromite. Use a hand lens to confirm luster and transparency. Pyropes often glow faintly when held against light, unlike most metamorphic garnets. Grids matter here. Label every sample site clearly and log results in a field notebook or app. If multiple samples return indicator minerals, plot them. A visual cluster, where several adjacent points all contain the same suite, implies proximity to source. Conversely, scattered positives or single-point hits usually suggest long-distance transport or contamination from human activity, such as road fill or mining tailings. At this point, some may be tempted to dig deeper, but resist that urge until you've verified the pattern. Random trenching or bulk sampling before verifying an indicator suite wastes effort and can ruin subtle depositional clues. If your indicators show consistency, especially upstream strengthening, you have reason to proceed. If not, move on. Importantly, one promising result doesn't mean you're close to diamonds. It means you're close to a rock type that might contain them. The next layer of testing brings more complexity. Tools that suggest diamond presence indirectly, but still leave room for error. The glow of a stone under ultraviolet light can feel like a thrilling discovery, until it leads you down the wrong path. Many newcomers rely on fluorescence as a shortcut to confirm diamond presence, but in the field, this approach generates more false positives than real finds. Understanding what UV light actually reveals, and what it doesn't, is essential for separating potential diamond-bearing stones from deceiving duds. Most natural diamonds do fluoresce under long-wave UV light, commonly glowing blue due to nitrogen impurities in the crystal lattice. This trait is particularly common in diamonds from certain regions, like South Africa and parts of Russia. But here's the catch. The intensity, color, and even presence of fluorescence can vary wildly, and several non-diamond minerals and synthetic imposters can fluoresce just as strongly or stronger. In field conditions, minerals such as calcite, scheelite, scapolite, sodalite, and even some feldspars can emit brilliant fluorescence, especially in sedimentary or metamorphic terrains. These materials are often mistaken for diamonds, especially when they appear as small, bright grains in concentrate pans or among loose gravel. Even quartz with slight lattice strain or certain coatings can glow under UV, mimicking the classic bluish hue of diamond. Then there's the problem of altered host rocks. Weathered kimberlite or lamproite may contain fragments that fluoresce due to secondary minerals, creating the illusion of a diamond-bearing signature when none exists. Worse, man-made materials, glass shards, industrial waste, or zirconia fragments, frequently end up in gravel stockpiles or tailings and can fluoresce vividly. A glowing fragment does not mean a valuable one. To reduce false positives, always pair UV inspection with at least 2 other diagnostics. Fluorescence should follow a heavy mineral indicator sweep and precede more definitive tests like thermal conductivity or specific gravity. Also note fluorescence pattern. True diamonds often glow more intensely at the edges, or show uneven luminescence due to internal zoning. Fake stones tend to glow uniformly, or with an exaggerated brightness that feels artificial. Carry a dual wavelength UV lamp if possible. Long wave, 365 nanometers, and short wave, 254 nanometers. Some imposters react differently depending on the wavelength, allowing better field discrimination. Record which wavelength triggers a response and how strong it is. Use a dark cloth or shaded tent to eliminate ambient light. Many weak fluorescers are missed in open daylight conditions. Critically, do not use fluorescence alone to make sampling decisions or discard material. More than one verified diamond recovery came from gravel that didn't fluoresce at all. Others came from samples that glowed intensely, but contained nothing of value upon further testing. So while UV light is fast and portable, it's a blunt instrument, useful only when interpreted with skepticism. A stone's true nature lies deeper, in its physical behavior and internal chemistry. That's where our next tool comes in. A probe that measures how heat moves through a stone. A much harder trait to fake. When visual clues and UV responses blur the line between real and fake, thermal conductivity becomes a crucial truth test. It's one of the most effective ways to separate actual diamonds from their many lookalikes. And unlike fluorescence, it's based on a physical property that's nearly impossible to counterfeit in the field. Diamonds are exceptional thermal conductors, dissipating heat faster than almost any other natural material. This trait stems from their tightly bonded carbon lattice, which transfers heat almost instantly across the structure. In contrast, most fakes, quartz, glass, cubic zirconia, topaz, and even most garnets, are relatively poor thermal conductors. The difference is so stark that a $20 thermal probe can reliably distinguish them in seconds. Using the probe is simple but demands clean contact. The surface must be free of dirt, moisture, and oil. Any barrier will distort the reading. Apply the tip gently to a flat facet or freshly broken surface. If the probe is diamond calibrated, it will trigger a specific visual or audio cue when heat flow matches the diamond signature. Most modern testers include a control for moissanite, which is the key risk at this stage. Moissanite, a lab-grown silicon carbide, conducts heat similarly to diamond and can fool basic thermal testers. It often shows the same quick dissipation response. That's why advanced models include electrical conductivity testing. Diamonds are electrical insulators, while moissanite conducts electricity. A dual-mode tester is best, especially when you're working with loose stones or fragments that could have originated from jewelry or industrial processes. One nuance: thermal testers require a minimum stone size, usually around 0.02 carats or larger, to return reliable results. For smaller grains or embedded crystals in host rock, conductivity may not register. In these cases, use it only as a supportive check once visual and indicator criteria are already pointing to something significant. In the field, thermal probes are most useful in dry conditions or mobile labs where recovered concentrates are screened before full processing. They offer fast triage. Stones that pass thermal and resistivity tests move on to lab verification. Those that fail get downgraded or discarded. But this tool also has a subtle second use. When testing broken matrix pieces from suspected kimberlite or lamproite, sometimes embedded diamonds near the surface give a brief thermal spike, especially in weathered nodules where erosion has begun to expose internal inclusions. These hits are rare, but when combined with positive indicators, they justify further subsurface sampling. Still, even thermal conductivity has its blind spots, particularly when evaluating unknown host material with embedded crystals too small or too deep to test directly. That's where another old school, yet precise, method comes in: specific gravity. Specific gravity, the ratio of a stone's density compared to water, is a field-proven technique for narrowing down candidates when visual inspection and thermal probes leave ambiguity. Unlike sparkle or fluorescence, density can't be faked, dyed, or enhanced. For diamond hunters, it's one of the most decisive, low-tech methods for identifying likely stones and filtering out pretenders. Diamond has a specific gravity of approximately 3.52. That puts it above quartz, 2.65, feldspar, 2.55 to 2.75, and most glass, 2.4. But below moissanite, 3.22, and garnet, ranging from 3.4 to 4.3 depending on variety. Kimberlite, the host rock, generally falls between 2.6 and 3.3 depending on alteration and mineral content. But fresh samples rich in olivine or magnetite can edge higher. By measuring Sg, you can assess whether a sample, be it a loose crystal or an embedded fragment, matches the density expected of diamond-related material. To perform the test, you only need a precision scale, 0.01 G accuracy, a small cup of water, a fine thread or wire, and patience. First, weigh the dry sample. Record this as W. Then suspend it in water without letting it touch the container sides and record its submerged weight as W2. The formula is simple. Sg equals W/WW2. For example, if a fragment weighs 1.75 G dry and 1.25 G when submerged, the Sg equals 1.75/1.75 to 1.25 equals 3.5. That's within diamond range. Anything below 3.2 is likely not diamond, unless it's a composite or heavily fractured. The same test can be applied to concentrated minerals from sieved samples. Dried garnet grains with an Sg greater than 3.9 may suggest almandine or pyrope, both valuable in tracking kimberlite dispersals. Ilmenite typically tests around 4.7 to 4.8, and chromite even higher, pushing into the 5+ range. These readings not only confirm mineral ID, but help estimate how far they may have traveled in water. Higher Sg means shorter transport, suggesting proximity to source. But beware of confounders. Porous or fractured samples can trap air, lowering the Sg artificially. Likewise, coatings, iron oxides, clays, or organic films can skew results. Always clean the sample thoroughly and, if possible, test multiple fragments for consistency. Specific gravity isn't perfect for final identification. It won't tell you what the stone is, only what it isn't. But as part of a combined testing strategy, it's invaluable. A grain that passes the Sg filter, fluoresces subtly under UV, resists a magnet, and shows poor electrical conductivity? That's a high-priority specimen worth professional evaluation. Yet as promising as this sounds, not all that's dense and shiny is worth chasing. Some stones that test well in every category still turn out to be imposters. And one in particular is designed to fool even the most seasoned collector. It's the stone that checks nearly every box: thermal conductivity, visual brilliance, hardness, and still isn't a diamond. Moissanite, especially its synthetic form, is the most persistent and convincing imposter in the diamond world. In the field, failing to recognize it can lead prospectors to waste time, money, and credibility chasing false positives that test like the real thing. Until they don't. Moissanite is composed of silicon carbide SiC, a mineral that rarely occurs naturally, but is now mass-produced in labs for both industrial and gem use. Its physical traits are close enough to diamond that even professional jewelers have mistaken one for the other. Moissanite's hardness is second only to diamond, clocking in around 9.25 on the Mohs scale, and it conducts heat well, enough to pass standard thermal probes designed to detect diamond. Visually, moissanite often displays more fire than diamond, a rainbow dispersion that's actually a giveaway under direct light. But in raw form, or when embedded in matrix, this difference is subtle. Some moissanite crystals, especially synthetic hexagonal types, can form as octahedra or other habits similar to diamond. Worse, many are found in gravel fills, tailings, or areas near industrial discard zones, where they masquerade as natural finds. The key diagnostic test that separates moissanite from diamond is electrical conductivity. Diamonds are excellent insulators, while moissanite conducts electricity. A dual-mode tester, capable of evaluating both thermal and electrical properties, is the best defense. These units are more expensive, but essential once you enter zones where diamond lookalikes are known to occur, or where the market for rough stones is active and unregulated. Moissanite's specific gravity is slightly lower than diamond, about 3.22 versus diamond's 3.52, but the difference is often within margin of error for small stones. Optical differences can also help. Under magnification, moissanite exhibits strong double refraction, visible as a doubling of facet edges or inclusions. Diamonds are singly refractive. Using a 10x loop on a flat facet or crystal face, this doubling can be subtle but decisive. Some prospectors have been lured off course entirely by moissanite-rich tailings, especially near industrial centers or in streams below artificial embankments where discarded lab stones can end up. These finds, though technically real crystals, have no value as natural diamond rough and often lead to false excitement and financial loss. The trap isn't just technical, it's emotional. A stone that passes test after test builds conviction. It pulls in investment. More gear, more digging, more lab submissions. That's why confirmation bias is dangerous in this phase. Only layered testing, thermal, electrical, SG optical, can diffuse the illusion. But sometimes, even when the stone turns out genuine, its origin throws the entire assumption into question. Because not all diamonds come from the volcanic pipes everyone's been chasing. Some are carried elsewhere, quietly deposited far from their source, hiding in the most unlikely places. It's a common assumption. Find indicator minerals, trace them uphill, and you'll strike a kimberlite or lamproite pipe. But some of the richest diamond recoveries on record didn't follow that model. Instead, they came from secondary deposits, placers, where diamonds were eroded from their source pipes and transported kilometers, even hundreds of kilometers, before settling in completely different geological contexts. The result? Diamonds in terrains where no pipe exists at all. This reversal can derail an entire search strategy, if not accounted for early. Imagine locating a promising cluster of pyrope garnets, ilmenite, and chromite in a stream system, only to grid upstream for weeks with no sign of a volcanic intrusion. The frustration mounts, until someone samples a downstream gravel bar and finds the diamonds sitting quietly, concentrated by water, completely disconnected from any intact pipe. These are alluvial or alluvial placer deposits, formed when diamonds weather out of primary host rocks and migrate into sedimentary traps. In some cases, glaciers or massive river systems move the stones tens of kilometers before deposition. The terrain might now be floodplain, marine terrace, or even arid desert with relict gravels. The source pipe may be deeply buried, eroded away, or located in inaccessible terrain far upslope, or even across national borders. Identifying a placer deposit involves looking at more than just the presence of diamonds or indicators. You must evaluate the depositional environment. Are the stones rounded or angular? Are they associated with high-density lag gravels or fine silts? Is there a noticeable size sorting? Heavies at the bottom, light silicates on top? These patterns tell you if diamonds were transported by water or gravity, and how far they likely moved. In Namibia, for example, some of the highest quality marine diamonds ever recovered were found in beach gravels, long after their host kimberlite pipes were eroded inland. In Canada's Northwest Territories, diamonds are found in glacial tills with no exposed pipe for kilometers. In Brazil, alluvial deposits on flat ridges, traced not by elevation but by remnant weathering patterns, yield stones when no volcanic rock is visible at all. The practical implication is this: If your fieldwork hits a concentration of indicators but fails to locate a pipe, do not assume failure. The signal may have originated long ago and far away. Instead, shift strategy, map sediment flow, analyze transport vectors, and target trap sites. Terraces, benches, oxbow lakes, and ancient stream beds buried under new deposits. Sampling at different depths in these zones can reveal stacked gravels where diamonds settled in distinct depositional events. This shift in logic, from pipe first to sediment first, marks a major turning point in serious prospecting. It expands the search area, but also demands tighter controls on data. Sediment origin, grain morphology, and mineral concentration gradients. What you thought was a dead end may instead be the tail of a rich dispersal plume. But to follow that plume, you'll need to benchmark your method against proven models. Processes that geologists and institutions rely on to systematically chase diamonds from gravel to certificate. Every verified diamond recovery, from casual field find to multi-million-dollar deposit, follows a version of the same structured pipeline. This workflow moves from scattered indicators to concentrated samples, through lab verification, and finally into valuation. Deviating from it increases the risk of wasted effort, misidentification, or missing a key opportunity. Whether you're a solo prospector or part of a formal exploration team, mastering this process turns scattered clues into defensible evidence. It starts with craton identification. Diamonds form under immense pressure, typically at depths greater than 140 kilometers, and only within geologically stable cratonic roots. Using tectonic maps, regional geophysical data, and published kimberlite fields, the first move is to restrict your search zone to Archean or Proterozoic-aged cratons. Anything younger or more tectonically active is almost certainly barren. Once in a viable zone, systematic sampling begins. Field crews collect sediment or soil samples at fixed intervals, ideally along drainage networks. Each sample, usually 10 to 30 kilograms, is screened down to the heavy mineral fraction using sieves and gravity concentration. This concentrate is sent to a mineral lab, where heavy liquids or dense media separation isolate grains of interest. Labs then examine these under binocular microscopes to count and classify pyrope garnets, chromite, ilmenite, and other indicators. Each grain is logged by type, color, morphology, and chemistry. This chemical step is critical. Not all garnets indicate diamond potential. Labs perform microprobe analyses to determine chromium and calcium content, key factors in determining whether a garnet formed in diamond stability fields. G9 and G10 pyropes, for instance, are closely linked to diamondiferous kimberlites. Similarly, ilmenites with high magnesium and low titanium correlate strongly with diamond-hosting pipes. Without these chemistry checks, field indicators remain ambiguous. If enough diamond-favorable minerals are found, especially in multiple adjacent samples, a tighter grid is laid out. Sampling intensifies in areas with high counts. At this stage, exploratory drilling may begin, often using reverse circulation or core methods to test for bedrock pipe material beneath soil or till cover. Drill chips are analyzed for mantle-derived minerals and, if kimberlite is confirmed, subjected to bulk sampling. Bulk sampling is where actual diamonds enter the picture. Tens of tons of kimberlite are crushed and processed through dense media separation plants to recover any contained diamonds. These stones, whether microdiamonds or larger specimens, are weighed, classified, and studied for quality indicators: clarity, color, morphology, and breakage. Only after this step does valuation become relevant. Without knowing grade, carats per ton, and stone quality, even a confirmed pipe has no market value. Labs submit recovered diamonds for valuation under standardized conditions, often in conjunction with major gemological bodies or government oversight programs. For independent field collectors, replicating this full pipeline may not be feasible, but understanding its components is crucial. Even collecting a few grams of concentrate and having them processed at a university or contract mineral lab can produce meaningful data. If you're able to provide verifiable indicator mineral counts and chemistry, your find becomes more than a hunch. It becomes evidence. Still, even the most rigorous method only works if you're in the right place. Some regions support this pipeline. Others, despite good geology, don't yield consistent results. Understanding the regional hit-or-miss pattern is the next step in making your efforts count. Diamond exploration is not evenly distributed across the globe. Some regions yield rich returns with minimal effort, while others, despite promising geology, consistently disappoint. Understanding where the standard pipeline actually works helps direct effort toward productive terrain and avoid decades-old dead ends. Geography, glaciation, tectonics, and even politics all influence which diamondiferous zones can be effectively worked today. Africa remains the cornerstone of global diamond production, with several standout cratonic regions. The Kopval Craton in South Africa and Botswana hosts dozens of kimberlite pipes, many of them high-grade. These include famous mines like Jwaneng and Venetia. Indicator mineral trails in these regions often yield strong positive results, with dense clusters of pyrope garnet and ilmenite that are traceable upstream to confirmed pipes. The region also benefits from decades of mapping, meaning new discoveries often hinge on revisiting old terrains with better tools. Further north, the Congo Craton and its satellite regions host secondary deposits, especially in the DRC and Central African Republic. Here, diamonds are often found in riverine gravels and alluvial contexts, rather than from direct kimberlite exposures. While grades can be high, logistics and political instability pose major challenges to sustained exploration. In Russia, the Siberian Craton, especially the Yakutia region, hosts the Mir and Udaknia pipes, among the most prolific diamond sources on Earth. These pipes are deeply rooted and formed through some of the most explosive kimberlitic events ever recorded. The cold climate preserves glacial tills and indicator trails exceptionally well, and state-supported geological surveys have mapped dispersal patterns in great detail. Independent exploration here is difficult but not impossible, particularly on the margins of mapped fields. Canada's Slave Craton, especially in the Northwest Territories, represents a textbook example of glacial transport masking rich diamond sources. The Akati and Diavik mines were discovered through painstaking indicator mineral work, with G10 garnets and eclogitic ilmenites spread across hundreds of kilometers of till. The challenge here lies in interpreting glacial movement. Diamonds were dragged southward by ice sheets, leaving misleading surface trails that require deep geological modeling to reverse track. Australia's diamond history focuses on the Argyle mine, sourced from a lamproite pipe within the Kimberley region. Unlike kimberlites, lamproites don't always produce clear indicator suites. Argyle's diamonds are small but high in volume, with a pink to brown color range that commands niche market value. With Argyle now closed, satellite fields in Western Australia are drawing renewed interest, especially those previously dismissed due to weak surface indicators. Outside these well-known zones, secondary and marine deposits form unique opportunities. Namibia's southern coast yields alluvial diamonds transported by the Orange River and concentrated in marine terraces. These are accessed via shallow overburden, using excavation more akin to paleontology than hard rock mining. Similarly, Brazil's São Francisco and Jequitinhonha rivers have hosted centuries of artisanal diamond extraction, often in flat ridgetop gravels with no nearby pipe exposure. Regions like India's Darwar Craton and China's North China Craton also contain pipes, but modern exploration is limited by overburden depth, land use, or insufficient economic grade. In the United States, scattered indicator finds in Montana, Wyoming, and Colorado have hinted at source pipes, but few have progressed past test drilling. Understanding where the pipeline works means knowing not just geology, but how terrain, erosion, glaciation, and access shape results. Many failures stem not from poor indicators, but from working a terrain that hides or diffuses the diamond trail too well to follow. But in some cases, it's not the geology that confuses, it's overlapping signals from other minerals. Jade, in particular, presents a recurring challenge, with its host rocks often mimicking or obscuring diamond indicator suites. In several terrains around the world, jade and diamond indicators appear side by side, not because they share a genesis, but because the host environments partially overlap. This creates confusion for field collectors who may chase the wrong signal, or worse, misidentify valuable jade as worthless when focused solely on diamond recovery. To navigate this crossover, one must understand both the geological and mineralogical signatures that separate true diamond indicator terrains from jade-forming zones. Jade occurs in two main forms, nephrite and jadeite. Nephrite forms in serpentinized ultramafic rocks, terrains that are rich in minerals like actinolite, tremolite, chlorite, and epidote. These rocks often weather to a greasy or fibrous texture, and can be found in similar settings to some weathered kimberlite or lamproite. When weathered, both nephrite and kimberlite may appear as greenish, massive, or waxy rocks with no visible crystals, leading to misclassification in the field. In particular, nephrite zones can host magnetite and chromite, minerals that are also part of the diamond indicator suite. This overlap is most pronounced in British Columbia, parts of Siberia, and Central Asia, where ultramafic belts produce both jade and indicator minerals. In these zones, finding black magnetic sands, dense garnet-rich gravels, or greasy green boulders doesn't automatically mean diamonds are nearby. It could simply mean you're standing in a nephrite-bearing shear zone. Even more deceptive are regions where jadeite forms, typically in high-pressure, low-temperature subduction zones. These terrains can also produce high-chrome pyroxenes and garnets, which visually mimic the diamond pathfinder suite. In Myanmar and Guatemala, for instance, jadeite-bearing serpentinite zones produce deep red garnets that, under low magnification, look like pyropes. Without chemical verification, a prospector could follow these false trails for months. The diagnostic difference lies in chemistry and context. Pyrope garnets from diamond terrains show specific CR and Ca ratios, which can only be confirmed via microprobe analysis. Nephrite and jadeite indicators, by contrast, show amphibole or clinopyroxene-dominant compositions. Magnetite in jade zones tends to form in banded iron-style textures, while ilmenite in kimberlite-derived samples appears as discrete, heavy grains, often rounded by transport. Field strategy must also change in these crossover zones. If you're in a serpentinized terrain and finding greenish massive rocks with fibrous fracture, test for toughness and translucency. Nephrite is tough, extremely resistant to breakage, and will often exhibit a waxy luster when polished. Diamondiferous host rock, even when altered, crumbles more readily and lacks that tough, fibrous feel. Use 6 sandpaper or a metal pick. Nephrite resists abrasion, while weathered kimberlite powders easily. Importantly, jade-bearing zones have their own market logic. Nephrite and jadeite can command high prices based on translucency, uniform color, and absence of fractures. A mistake in discarding jade material because it isn't diamond can result in major lost value, particularly in artisanal fields where both materials coexist. Understanding these overlaps helps refine search areas. If indicator minerals appear in a terrain with serpentine boulders, ultramafic dikes, or amphibole-rich schists, don't just chase diamonds. Evaluate the potential for jade recovery. In some parts of the world, the jade is more valuable than any rough diamond you're likely to recover. Still, both materials tend to occur in challenging terrain, steep slopes, unstable outcrops, or flood-prone valleys. Knowing what you're walking into physically is just as important as the geology itself. Diamond-bearing terrains often lure prospectors into areas that pose serious physical risks, especially where steep slopes, unstable ground, or sudden storm surges can turn an ordinary sampling run into a survival situation. The geology may be promising, but it's the terrain's hydrodynamics and structural integrity that determine whether you can work safely, recover material effectively, or even return the next day. Many kimberlite pipes are exposed or eroded into visibility along slopes and escarpments. Over time, weathering weakens the surrounding rock, creating loose scree fields and colluvial fans. These deposits may carry valuable indicator minerals or diamond fragments downslope, but they also hide unstable footing, hidden voids, and the ever-present risk of rockfall. A misplaced step near a decomposing ultramafic outcrop can lead to a slide that buries equipment, or worse, people. In placer zones, especially in tropical or alpine settings, the danger escalates when water is involved. Narrow ravines and dry washes might seem harmless in fair weather, but a storm upstream, even one you don't see, can unleash flash floods that tear through sampling zones with zero warning. Diamonds are dense, but so are boulders, and a high-energy flood event can wipe away your grid, your gear, and your sample trail in under an hour. Rainfall also changes sampling chemistry. A calm gravel bar one day may become muddied,